Well, thank you very much for that very nice introduction. So I'm very pleased to be here. I'd like to thank the organizers for inviting me. And I'd like to talk to you about racetrack memory, and in particular 3D racetrack memory. So of course I want to introduce what racetrack memory is before going to the 3D version. And I wanted just to acknowledge the co-workers in my institute who've contributed to this work. And in green, these are the ones who've contributed to the 3D racetrack, and well, 2D racetrack. And in purple, these are the ones who've contributed to cryogenic racetrack that I want to briefly discuss. And then I wanted also to mention that Haoji Zhang, who's a group leader in my group, and Cheng Gedong, who's a PhD student, are both here. And if you're very interested in how we use STED multiphoton lithography, then they're the ones you could discuss in more detail about the details of the method that I'm going to discuss briefly. So just to remind you, what is racetrack memory? And racetrack memory is a concept which is innately three-dimensional. This was my original proposal, that we will build these vertical nanowires, and then in the nanowire we magnetize regions in one direction or the other, the blue and red, and then we store the information in the form of the magnetic domain walls that separate these regions. And on the nanoscopic scale, these domain walls can be as little as a few nanometers wide. And the concept is we move the domain walls around the racetrack using current pulses. And this current pulses then enable us to move a series of domain walls synchronously back and forth so that they can access reading, writing devices. In this way, we can store perhaps 100 domain walls in the same area of a silicon wafer where today we store 1 bit. So we can increase the storage capacity compared to any conventional memory today by maybe 100 times. And we believe that we've now achieved that, at least in the laboratory. So I want to briefly discuss those recent developments. I'm not going to really discuss how this technology has evolved. It was certainly a concept I had in 2002, and we first demonstrated in the first version of Racetrack that we could move soft domain walls in soft magnetic materials, where the structures are very different from the structures in perpendicularly magnetized materials. They consist of large vortex and transverse walls whose size can elongate dramatically from a few hundred nanometers to microns as you manipulate the domain walls. Then we introduced perpendicular magnetic anisotropy by multilayering cobalt and nickel layers, each layer just a few angstroms thick, and we demonstrated one can achieve velocities actually similar to those in these very soft nickel cobalt iron materials, about 100 meters per second, but they're driven by the so-called spin transfer torque. And then eventually we switched to this spin orbit torque, where we demonstrated in this case that using the spin Hall effect we could transfer electrical current into transverse spin currents, and then the spin currents diffuse into the magnetic domain walls, providing torques that are more efficient than spin transfer torques by a factor of 3 or so, enabling the domain walls to move somewhat faster and actually in the opposite direction. And then finally, in 2015, we demonstrated in a synthetic anti-ferromagnetic racetrack where we put 2 racetracks, one on top of each other, separated by a very, very thin layer, was ruthenium at the time, that couples these 2 layers anti-ferromagnetically. And this is critically important for all magnetic nano devices, that you need to eliminate the stray fields that you can see the domain walls produce. And those domain walls, we showed by simulations, interact with neighboring racetracks, preventing dense racetrack memories. In fact, if you don't eliminate these stray walls, you cannot build any type of magnetic nanosensor or magnetic memory. And in fact, this synthetic antiferromagnet was something I proposed a long time ago in the 1990, 1991, and was used in IBM's first spin valve sensors, and subsequently in nearly all magnetic random access memory devices. So this is the sort of brief history I'm not going to really talk about in any more detail, but I think it's now even more exciting today. So we heard this morning a little bit about domain wall pinning, and you might imagine that as we shrink the width of these racetracks, the domain walls might be pinned by, for example, line edge roughnesses. And originally, most of the work I showed you in the first foil was accomplished using racetracks that were several microns in width, so we could use Kerr techniques to detect the racetrack. So here, for example, racetrack, it's nearly 2 microns wide. We look at a single domain wall, we apply current pulses, the domain wall moves, and we detect the motion by static imaging using Kerr microscopy techniques. And then we can shrink the width, to 1.4 microns, and so on, all the way down to 200 nanometers. And even then, even though it's sub-wave, deep sub-wavelength. Nevertheless, we can detect the domain walls, and you can see and we can see the domain wall motion. In this way, we can measure the velocity. We simply detect the motion versus the integrated time. We've applied these current pulses, and typically we use current pulses on the sub 1 nanosecond to a few nanoseconds long. And then what you typically see, the velocity of the domain wall as a function of the intensity of the current pulse. You first see you need to apply some critical current density to move the domain walls at all. Then the domain wall velocity increases and eventually saturates. And here you can see in a single ferromagnetic racetrack, which is formed from these 3 layers, cobalt, nickel, and cobalt, that's just 10 angstroms thick altogether, you can see the domain walls move at velocities of about 150 meters per second. And if we make synthetic anti-ferromagnetic racetracks, the velocities will be much bigger. So the most important point here is that the threshold current, this critical current to move the domain walls, actually changes very little as we decrease the wire width. So we go from microns to 100 nanometers. It changes by a factor of 2, which is very modest. So what does that mean? That means that these critical current density, which theoretically should not exist, actually is caused by variations in the magnetic properties within the bulk of these layers. Most likely because you can see these layers are so thin that small variations in thicknesses, which are inevitable, will give rise to change in local anisotropy and magnetization. And this gives rise to an effective pinning, which is actually quite weak, nevertheless. Turns out that for applications, I mentioned vertical 3D racetrack. Turns out we're working with Samsung. Samsung provides some funding for the last 4 years, actually. And their original idea was they wanted us to demonstrate we could use racetrack in a 2-dimensional form, but put them one on top of each other. And they want to use this to replace VNAND, which is the densest form of flash memory today, which is Samsung is a world leader in that technology, but it's already scaled to dimensions which cannot be scaled further. Anyway, so what we had to do was to demonstrate we could reduce the threshold current. And so we were able to do that by a factor of 10. And we did by introducing different underlayers, no longer platinum, but if you use this very interesting material, iridium aluminum, it's the so-called L10 structure where you have alternating layers of iridium and aluminum. In fact, it's one member of an enormous family. And all of these materials can be made at room temperature by sputtering, and they automatically form this fantastic atomically layered structure, one atomic layer of aluminum, one of iridium. And by optimizing the composition, we could optimize the scattering, the spin-dependent scattering, and therefore generate huge spin-Hall angles, in fact, 10 times larger than platinum. This accounts for the reduction in this critical field. So this, I think, is very important. And also shown here, then we could use little dusting layers, thin layers of platinum, also similarly will change the critical current density because we reduce the magnetic anisotropy, which is not so favored. Well, that's just by way of introduction. Now I want to say we can also then go from, as I showed you, we could measure optically domain walls in 200 nanometer wide racetracks, but that's not technologically relevant. So what do? We've then developed, this is work by Jae-Chun John, we've developed, and Andre Miglioni, we've developed racetracks now, which you can see here, 70 nanometers wide, but we pattern in this case, platinum, underneath the racetracks. So here's can you see, this is the cobalt, nickel, cobalt racetrack. It's only 1 nanometer thick. And these platinum, we have, you can see the platinum layer underneath is slightly wider, and we have platinum electrodes. So we can measure the anomalous Hall signal. But by engineering the shape of this platinum wings, we can actually use the anomalous Hall signal generated at this electrode to detect the domain wall up to 20 times further away. It depends on the details and the engineering of this patterned platinum underlayer. So this is fantastic. And what we can then do is we can measure a single domain wall moving along this 70 nanometer wide racetrack as we apply these iterations, the number of current pulses. So you can see the domain wall moves continuously along the racetrack. We change the direction of current, it will move continuously back. We increase the intensity of the current, it takes less numbers of iterations to go from one end to the other. But you can see we can follow individual domain walls in these sub 100 nanometer wide racetracks, and they essentially move along the racetrack without any pinning, which of course is really important. And in this way though, because of these Hall probes, the current density here will be slightly lowered. So we can position the race individual domain wall very precisely along the racetrack wherever we have these Hall electrodes. And this is also very nice, and so in this way we can position individual domain walls with an accuracy of a few tens of nanometers, separated from each other by about 100 nanometers. These are exactly the technologically relevant length scales. If we can do this, and if we can, as I said, have a low enough critical current density, we could use Racetrack in a horizontal form to replace today's VNAD. So this would be a major achievement. However, that's 2D Racetrack. So we want to go beyond. We want to make 3D Racetrack. And of course, this is the topic of this workshop. We had some fantastic talks today. So I don't need to say very much at all. But we have 3 approaches to making 3D Racetrack. I'm only discuss 2. This one was already mentioned by the speakers this morning. And I think this is some very nice work by Kay Ger, who's a PhD student in my group. And what he did was to use this very elegant technique. You take a layer, in this case we're using this strontium-3 aluminum-206 that was really most recently pioneered by Harold Wang at Stanford University. This is a water-soluble oxide. And the idea is on a 1 centimeter by 1 centimeter magnesium oxide substrate, we grow this by pulsed laser deposition, and on top we grow our ferromagnetic racetrack or a synthetic anti-ferromagnetic racetrack. So the ferromagnetic, again, is just platinum, 2 nanometers thick, 3 angstroms cobalt, 7 angstroms nickel, 1.5 angstroms cobalt, and the synthetic antiferromagnet, we make 2 copies. Now what is amazing was that he could deposit this on top of our strontium aluminum oxide, and then you dissolve from the edges this oxide layer, 1 centimeter by 1 centimeter, and then you take that very thin membrane, including the racetrack, and on the surface of water, he takes this and then transfers it onto another substrate. And the substrate we've pre-patterned to have, okay, we have these structures like this is in sapphire. Structures can be almost anything. And we pre-pattern them in this case to have this kind of hillock structure. And then what does he do? He takes the membrane and places it on the top, and it will conformally follow this structure. Actually, it really does work. And this is, you can see here, very beautifully in this cross-section TM. You see this black line, that's that racetrack. It's just a few tens, 2 or 3 tens, 10, 20 or 30 angstroms. So wide, that's amazing, right? It then follows the hillock, but not exactly. So you see this is, you see it's real, right? It must be real. So that's amazing that it works. And then what he could show was that we can see the current versus current, velocity of domain wall versus current in this. This is the freestanding layer before he did this technique. And this is after he's placed that thing on protrusions up to 1 micron tall. And you can see in the case of the single ferromagnetic layer, the critical current density has increased slightly. But however, if we make a synthetic anti-ferromagnetic layer, then you can see the freestanding layer before we did anything, or he did anything, and after manipulation is basically the same. So that's amazing. So it's moving at a few 700 meters per second, which is pretty fast, even though we've grown this 3-dimensional racetrack. This is one approach we're using. We think this is the first 3-dimensional racetrack. Next, we heard this in the tutorials this morning, so I don't need to discuss this at all. We've developed our own multiphoton lithography capability. And this is work by Andre Farina, another PhD student of mine, and his PhD was to set up a super resolution microscope using this thing called STED, which is stimulated emission and depletion, to make a very fine optical beam which is less than the diffraction limit. As you know, this is, the pioneers of this technique won the Nobel Prize a few years ago. And we bought from one of those, he's actually a Max Planck director from his company, we bought a STED optical microscope. And now this is, I don't know if this is a video, the other one didn't work. See, this one works, this is from Andre, and you can see, can you see? Some are not working. Anyway, if you saw, you would see this optical beam would be moving across, and what happens is we move it in steps, which is half the resolution of our microscope. The resolution of this microscope is 50 nanometers. That is the voxel size. using this fantastic super resolution technique. Well, this is all Andre's work. And what he can then do is build structures. So you basically put a droplet of a photoresist, which has a rather complex structure, and you use a photo initiator to initiate polymerization within that photoresist using a negative resist. So wherever the optical beam is, the focal point is, we polymerize it to cause a structure of the order 50 nanometers wide. And then he can, by moving the laser beam around, using, as we heard this morning, either using piezo stages or mechanical stages for the larger structures, he can build complex structures in 3 dimensions, as shown here. These are just simple examples. The surface roughness, in our case, I asked that question this morning, is about 0.3 nanometers. So these are pretty smooth structures, so it's very, very nice. Of course, it depends on a lot of details. And I also wanted to point out that Andre went beyond any existing microscope, as far as we know, and by incorporating a fluorescent signal. So we have several different lasers. I'm not going to discuss, you need 2 lasers for the STAD and another laser to detect the fluorescence, to fluoresce this molecule. And so basically he makes on-the-fly corrections because the polymer, it's a liquid, it's polymerizing, and this is without any corrections. But after he corrects using this luminescence to basically tell the computer system to move the laser beam slightly differently, then he can build structures that are more perfect. So we believe this is, again, a major advance in this technology. And Andre now has finished his PhD and is actually working for NearSpec, from which we bought the microscope. So this is fantastic. So again, what can we do then? We basically use this, it's complicated, I have to say, lots of laser beams, lots of stages, so it's non-trivial. Nevertheless, it's the world's, we believe, the most advanced system of its type. It's better than nanoscribe by several times, 10 times, 100, well, anyway, much better, order of magnitude better. And so we can build complex structures. What he's done then is to build structures on which we're going to build scaffolds. We heard this morning from Emilio, we can build scaffolds, and then we're going to deposit using sputtering the racetrack, exactly the same racetracks I just showed you. Here is the structure we're making. This is with, this basically, can you see it's like a bridge? We have some ramps, we have a surface, there's a hole underneath, and these are V-shaped structures so that when we deposit materials on top, we automatically can make electrical contact to the racetrack without the need for any other lithographic post-patterning, which we think is very important. And so in this way, and at the same time, what we're interested in then, as we heard this morning in Dennis's talk, for example, is how we can generate curvature and use that to generate new forms of exchange, DMI exchange, that will interact with the exchange, the DMI exchange within the platinum, cobalt, nickel, cobalt structures. And so here we've introduced, you can see a torsion. So the structure actually bends one way, bends back again. For technical reasons, we need the surface to be flat at both ends so we can easily electrically connect to it without any additional lithography. Nevertheless, it's unimportant. We have 2 regions. We can twist it one way or we can twist it the opposite way. And what we find is, very interestingly, we then deposit on top of this our complex racetrack, platinum, cobalt, nickel, cobalt, each just a few angstroms thick. And what does he find? He finds then that if we have an up-down or down-up wall, they move at different speeds. They have different critical current densities for motion, and the one that has a smaller critical current density will also go faster. In this way, we can build essentially a diodic structure. So I'm not sure let's see that. So that's basically the idea. This is a foil from Andre, where he just shows you in the cartoon. We make these 2 structures, one twisted one way, one twisted the opposite way. And what we will then find is that these domain rules of up, down, up characteristic will travel through this structure with different velocities and have different critical current densities. So effectively what we've done is to build a diode. So I think in this, if it works, if these, oh yeah, can you see? These ones seem to be working. So you can see then, in this case, can you see clockwise torsion? You can see this domain wall moving through, and then you can see the counterclockwise, the same kind of domain wall doesn't move through. So you can see, so it's like a diode. And it's because we've created, through this torsion, an additional curvature. Curvature creates a new DMI exchange, which competes or adds to the DMI exchange innate to the structure itself. So we basically can have a competition between the geometrical and spin chirality in this way. So we think this is very, very interesting. This is the second three-dimensional racetrack. Now, the third racetrack approach we're using is to use atomic layer deposition. So Halle here is an expert. He's been working on this. It's non-trivial. In fact, he's the third person in my group who's worked on this. He's the only one who's made it almost successful. And now we can actually atomic layer deposit the cobalt-nickel layers, a few angstroms. Normally in ALD, we're talking about 10 nanometer thick layers. So this is the first time this has been demonstrated to our knowledge. And once we've done this, we can really create this three-dimensional racetrack on vertical walls. This is our goal. We expect to achieve that shortly. Now, this morning, there was a very interesting discussion about the role of superconductivity. So in the last few moments, I want to switch to superconductivity and proximity effects, because we want to build a new type of racetrack that will operate at cryogenic temperatures. Of course, it could be three-dimensional. It could also be two-dimensional. And so just to remind you what happens when you place a superconducting layer on a ferromagnet, then as you all know, in conventional superconductors, the superconducting state is formed by Cooper pairs, two electrons with opposite spins and opposite momenta. However, in a ferromagnet, you obviously realize that the conduction bands are spin split by the exchange energy. This means to form a Cooper pair, you need to combine two electrons with opposite spins and have slightly different momenta. Therefore, they have a finite momentum. This leads to an oscillation in the superconducting order parameter, both with the conventional S wave nature, but also now there is a spin triplet component. And this spin triplet component is super interesting because it could carry, just like conventional spin currents, angular momentum, if it's in the correct S equals 1 or S equals -1 state. That's what we want to achieve. And I want to just show you, I think, how much time do we have? Oh, 3 minutes, so there we are. I want to show you how we could do that in a highly abbreviated form, but there we are. So what happens is, this was work by Bozdin 40 years ago, and then Sébastien Bergeret came up with this concept, okay, to sustain the triplet supercurrents, you need to introduce them into a system with non-collinear spins. So the idea here then is, as shown here, this is some work by Ivan Kindiak, a PhD student in my group, and Swapna Mishra, a postdoc. The idea is that let's take a vertical Josephson junction, two superconducting layers separated by copper from a magnetic material. Here it's the same magnetic material as in our racetrack nickel-cobalt multilayer. What do you find? This we call it a singlet structure. If we measure the critical current density above which we suppress superconductivity through this junction, then you can see in the singlet structure it's much lower and decays quickly with increasing thickness of this magnetic material than as compared to what we call this triplet structure, which follows Sébastien Bergeret's prescription. We actually have more magnetic material. You see, we add this nickel layer, which is in plane on both sides. Now what happens, this triplet current, in principle, this layer is below the length which completely suppresses superconductivity. It will have a triplet component which can then travel through this perpendicularly magnetized material. This is in plane, this is out of plane. The idea is a non-collinear spin texture will sustain superconductivity because of the triplet nature over long distances. This is what we see here. This structure, even though it's got a lot more magnetism, the critical current for superconductivity is much higher and decays much more slowly with increasing thickness of this magnetic material. And I just wanted to point out then we could also do the same thing. This is something we showed 2 years ago. This is okay, this I'm not going to show. This is what we showed here. So if you take this particular chiral antiferromagnetic material, then this system automatically has a non-collinear spin texture. And we demonstrated for the first time that spin triplet supercurrents can propagate through this system over long distances. So if there's finally time, then I want to just get back to cryogenic racetrack. And I want to show you we're actually making a lot of structures in which we make lateral Josephson junctions. Let's say this could have been this chiral material. I'm not going to talk about that. Chiral antiferromagnet, manganese-free tin, manganese-free germanium. Here are these superconducting electrodes. So what's amazing is you can introduce supercurrent from this material, and it will propagate through non-superconducting materials and be extracting through a second electrode. And we've demonstrated now we have materials where this spacing can be 1 micron, which is enormous. Very, very interesting. And I just want to tell you this one result then, which is one of the materials we've looked at, is something relevant to racetrack. And this is work by Kunrock John, postdoc, now he's back in Korea as a professor, where we take niobium. Well, this is manganese-free germanium. Okay, I don't want to talk about that one. I want to talk about, if there's time, I'll come back to it. We can use platinum. And platinum is much more interesting. Okay, maybe I accidentally killed that slide. Nevertheless, the idea is we take platinum, but we do it in a very clever way. We grow it on YIG. And the YIG, which is insulating, magnetizes the platinum in a direction perpendicular to the supercurrent. In order to see these effects, we need to have a material that breaks crystal center of symmetry and time reversal symmetry. For technical reasons, I don't have time to discuss that. Nevertheless, you can see here the type of behavior we see is, you see, current is flowing through, in this case, this manganese-free germanium at 0 voltage until we reach a critical current. And that's the basic concept. And we can do this with a whole variety of materials. And then what can we do? We can build what we want to build, a cryogenic racetrack. Unfortunately, currently the notion is two-dimensional, could be three-dimensional. And the idea is we're going to create triplet supercurrents that carry angular momentum, inject that into the racetrack, which will move the domain walls. Now, as I mentioned before, our racetracks typically use platinum. What can we do with platinum? We have a new idea, a new discovery. We discovered something called the Josephson diode effect. We can build a sensor which is innately ultra-low energy based on this new diodic effect. And that is the foil I wanted to show you, where instead of manganese-free germanium, we separate the niobium superconducting electrodes with platinum. But to break time reversal symmetry, we grow the platinum on, you're all familiar with YIG, which is a ferromagnetic insulating material. But if you magnetize it in a big field, go back to 0, we can have the magnetization pointing, let's say, in this direction, perpendicular to the supercurrent. Then on top, the niobium will make the platinum superconducting by proximity, and these two proximity effects combine to give a diode effect. And that means that if we measure the current, the critical current above which we suppress superconductivity, you see the voltage is 0, then it becomes finite. This current flowing in one direction, you can see is different from that critical current flowing in the opposite direction. This can then act as a sensor in our racetrack. If the domain points in one direction, we will see a supercurrent flow in the opposite direction. We would not. This is the only way to do it, and this difference in critical currents is up to 45% at 2 degrees Kelvin. Giant effect. So I see the chairman is getting very, very worried. So I'll skip this last foil and go straight to the conclusion. So 2D racetrack memory has evolved tremendously over the last 20 years. Nevertheless, looks super exciting now in our most recent work, where we've demonstrated sub-80 nanometer wide synthetic anti-ferromagnetic racetracks, velocities of 800 meters per second. And we've demonstrated we can see individual or sets of domain walls, which might be important for neuromorphic computing, by 1 or more, up to 16, anomalous Hall effect detectors built into the racetrack. And I wanted to, in particular, point out the domain wall pinning is independent of the width. It's very interesting. And I showed you how we could form a 3D racetrack on flexible membranes. That was work of Kegu. And using multiphoton lithography, the work of Andrea Farina, we built what we believe is the world's most advanced multiphoton lithography system, including using luminescence to correct the structures on the fly. And we built structures in which we can demonstrate the geometrical torsion, clockwise or anti-clockwise, influences the motion of the chiral domain walls. It would not otherwise be the case. And then finally, I want to give you a glimpse. Much of our work today is on building a cryogenic racetrack memory using two new phenomena. Supercurrents, which are triplet, that we want to use to manipulate domain walls. This has never been demonstrated, and then we want to detect them using this Josephson diode effect that we have discovered in several distinct systems over the last 2 years. I'd like to thank you for your attention.